Hello world, it's Suraj, and today we're going to build a blockchain in 5 minutes using Python. Ready? Let's get started. A block is a data structure that contains data and some attributes. Blocks can be linked together to form a chain of blocks. This is called a blockchain. The Bitcoin protocol uses a blockchain data structure to store transaction data, but we can store any kind of data in a blockchain. To understand how it works, let's code our own in the browser together using Google's Colab environment. We'll also periodically view a blockchain demo in the browser as well while we code for better comprehension. This will be a 4-step process. Import our dependencies, create a blockchain, then print out the blockchain. First, we'll want to import datetime so that we can generate timestamps for each block. We'll also import hashlib since it contains an important algorithm we'll use to define our block. We can define our block as a Python class, then define its attributes. Each block has 7 attributes, and we can list each as a distinct variable. First, the number of the block, so we can index each of them. Next, the data we'll store in this block. Bitcoin's blockchain stores transactions in here, but we'll just store text strings in here for simplicity. We'll define a pointer to the next block as well as the hash of this block. A hash is a function that converts data into a number within a certain range. The hash serves as both a unique identifier for a block and verifies its integrity. More on that in a second. We'll define a nonce, or number only used once. We'll later use it to help compute a unique hash for our block. Then we'll define a previous hash, which will store the hash of the previous block in the blockchain when we actually build a blockchain. And lastly, we'll define a timestamp for a block using the datetime library. Now that we've defined our attributes, we can write the init function for our class. It defines how we initialize a block, using some provided data as the only parameter. We'll also need to define a hash function for a block. The hashlib library contains the popular SHA-256 algorithm, which generates a unique 256-bit signature that represents some piece of text. The input to our algorithm will be a concatenated string that consists of 5 of our block attributes. See how a hash is created using the unique attributes of a block? This means that if someone tries to change the hash of a block in a chain of blocks, every block after it is changed, since each block's hash is generated in part using the hash of the previous block. And before we finish our block class, let's write a small print function that will print out the value of a block. Now that we've defined our block class, we can define our blockchain class. We'll define 2 key attributes of our chain of blocks, or blockchain, first, the genesis block and the head. The genesis block is what we call the first block in a blockchain, and we'll store the string genesis inside of it. The head will be the newest addition to our block. As we add more blocks to our chain, this head will be updated. Speaking of adding blocks, let's write our add function. This will add a given block to the chain of blocks. The block to be added is the only parameter we'll need. Blockchains are just glorified linked lists. We can set the hash of a given block as our new block's previous hash, and set the block number of our new block as the given block's number plus 1, since it's next in the chain. Then we'll set the next block equal to itself. This is the new head of the blockchain. We now have one more function to write, the mining function. This is what lets nodes in a network that don't necessarily know each other come to consensus on what the one true chain of blocks looks like, a chain that is immutable. It requires computing power to mine a block. This is a defense mechanism. In Bitcoin's blockchain, an attacker would need the majority of the computing power in the network to modify a block and give themselves money they don't rightfully have. In the Bitcoin network, 51% of the computing power is more computing power than the 500 fastest supercomputers in the world combined. And since no one has anything close to that much computing power, the network has survived for almost a decade now. We'll need to define 3 additional attributes in our blockchain class. The max nonce, which is 2 to the 32nd. It's the biggest number we can store in a 32-bit number. Then a mining difficulty. We use the mining difficulty value to compute our target hash. It's going to be 2 to the 256 minus our difficulty. In our mining function, we'll determine if a given block, which we'll input as a parameter, can be added to the blockchain. For a range of numbers from 0 to 2 to the 32nd, our max nonce value, we'll check to see if the value of the given block's hash is less than our target value. This is exactly what Bitcoin's mining function does as well. If it's less, we'll add that block to the blockchain and break out of the loop. Else, we'll increment the nonce and repeat the process until we reach the end of the loop. The mining difficulty sets how computationally expensive it is to mine a block. The higher the number, the longer it will take to mine, and the value of the nonce after mining reflects that. Now that we've defined both classes, we can initialize a blockchain. Then we'll write a loop to mine 10 blocks. Each of them will be initialized by a unique string. Finally, we'll print out each block in the blockchain. If we compile this code, we'll see each block in our blockchain with its associated attributes, including the unique hash, the data, and the timestamp.